So no.
Justo me estaba una noticia que parla de una
So there is this example. Yes, yes, click. So there is how much time?
50 minutes.
50.
Yeah. Let's go away. All right, I guess at this point no one else is going to turn up. All right, so our speaker is Gilberto from the University of Siegen, who's going to tell us about QCD-factorization amplitudes from SU3 symmetries.
Right. So well, thanks a lot, everybody. So thanks a lot for the invitation. Finally, it worked in person. It's actually my first seminar in person since 2020. So it's 2 years since. So the talk may be a bit technical, but if I understand correctly, in the public there are people who have worked on QCD factorization. I'm going to give also a brief introduction of stuff so that I hope everybody can follow what I am trying to explain. So this is the talk that comes from this paper. I work with Tobias Huber, who is also Siegen. Okay, so then things don't move. Okay, let's see. So I have to count or move from. I see. All right, so I'm going to talk about the meson decays. So a meson is a bound state of two quarks, one of which is the bottom quark. And here I am showing three different possibilities. So you couple the big quark with a light quark, a down, straighter, and up. So that's the basic setup. So we are always going to think about initial states where there are p mesons. So it can be any of these three guys. Something important to notice from now onwards is that I always take a light quark. For light quark, I mean a down quark, an S quark, or an up quark, together with an anti-B in this case, or you can take the CP conjugate as well. So just for you to notice, the mass of this bound state is coming mostly from the mass of the bottoms. The mass of the bottom is roughly 4 GeVs, and the mass of these guys are probably in the ballpark of 5 GeVs. I'm going to concentrate, so there are multiple final states in which a P meson can decay, and I'm going to focus into states where there are no leptons, so only mesons. And also I'm going to focus myself to cases where these mesons are light mesons. By light, I mean mesons that can only be made out of the up, the down, and the strange, and the anti-particle versions of these quarks. So you can establish an SU3 symmetry, SU3 flavor symmetry. So flavor because it comes from these three flavors of quarks. Okay, so then in the final state, we can have, for instance, pions or kaons or eta mesons. So you are taking essentially a light quark that is denoted here by Qi, and the conjugate of it. As I said, we are thinking in terms of SU3 symmetry, SU flavor. So these are the three possible states of this Qi. So that you take Qi and you tensorize that with the CP conjugate. So then you get an octet plus a singlet, and the octet plus the singlet. Sorry, here it should be plus. This should be plus instead of, so here you are calculating the tensor product, but it should be a plus instead of a cross. So that's my mistake. So the octet plus the singlet can be arranged in this matrix. So this matrix contains the possible values that this P in the final state can assume. So I'm going to consider only cases where the P meson goes into two like pseudoscalar mesons. Those pseudoscalars are precisely the ones shown in this matrix. So for example, you can have P plus going to pi naught, pi plus, or P plus going to pi naught, K plus, or B naught, D going to K plus, K minus. Okay, so then they're going to deal with a P meson in the initial state and two pseudoscalar like mesons in the final state. You can draw diagrams associated to these transitions. So I am showing you here all the possible transitions that you can have. The underlying quark level transition for the bottom quark is the one showing here. So, so all these decays are triggered by this underlying transition for the bottom quark. So the bottom always goes to a UU bar and a Q, and the Q can have values either as a D or as a stretch. So even though this transition seems quite simple, you can have a big plethora of final states, because you have also consider the expectation. Okay. Now there are very interesting mathematics. I mean, the amplitudes have very interesting mathematical properties based on all these requirements I just described to you. So the basic physical amplitude, so this is a template for the physical amplitude that can that describes all the decays I showed to you before. They are roughly 34, if I remember correctly. So these 34 decays, all of them have can be described by the same template. So that's quite interesting. This has to do again with the symmetries. So the physical amplitude can be decomposed in what we will call a tree subamplitude and a penguin subamplitude. This is the notation that is used in the literature. It's a bit misleading because that suggests that in the P contribution you only have penguins, and in the tree you only have trees. But that's not true. The tree can also contain penguins. So the leading difference between this P and the P is the Siegen structure. So the P is always going to be associated with lambda U, where lambda U is a product of B. So you have the Siegen B, U, U, and you can have either a down or a stretch. And because of the unitarity of the Siegen matrix, and because of the fact that you have three types of R-type quarks, you can write this relationship. So at the end of the day, as I said before, there is a generic template, and you can split this amplitude into sectors depending on the Siegen structure. So one of them is going to be associated with this lambda U, and the other one is going to be associated with the lambda T. Essentially, you have something with lambda U, lambda T, and lambda C. But because of this relationship, you can always write the physical amplitudes in terms of only two lambdas that encode all the Siegen structure. So that's the key message of this slide. So the amplitudes can be split in two sectors, and these two sectors, what I call E and P, are different depending on the Siegen structure. You can always find two Siegen factors and then factorize this amplitude depending on these Siegen quantities. So one of them is going to be lambda u, the other one will be lambda t. I try to explain briefly how these are constructed. So it's a very common notation in the literature.
What is TDA? What does it mean, TDA?
Which one?
TDA.
P.
TDA.
This one here.
TDA, the subscript that you put there.
TDA.
Topological
Distribution. Topological decomposition amplitude.
Topological decomposition
Amplitude. Yes, just a notation. I will explain that now. I mean, soon. So it's just that, I mean, the key message here is that you can always decompose this depending on the Siegen instruction in two parts. And you're going to have the up and the top. I mean, if you write this completely, you have up, top, and charm. But because of this unitarity relationship, you will always have only two of them. So you can minimize the amount of terms. So the top and the charm can be related using this one. And this is just a notation because you have different languages for this amplitude. So now it comes to the description in more detail. So as I said, the idea is that you have this SU3 flavor symmetry. Okay, the initial state is written here, and if you take the B meson or the anti-B meson and you combine that with an up, you get this B plus. You combine that with the down, you get this BD naught. You combine that with the S, you get this BS0. So all the three initial states can be very conveniently arranged in a vector SU3, in an SU3 vector. So that's quite nice. So this BI just refers to this vector in components. So, okay, now you're going to have two pseudoscalars in the final state, meaning that you have to consider two of these guys, because as I said, these metrics encode all the final states at once. So when I took this QQ bar and tensorize it, I said that I can write that as an octet plus a singlet, and that octet plus a singlet can be written with this matrix. So the final state this P in the final state can be written economically in terms of this matrix.
So let me ask you.
Yeah.
So I see too many etas in my case here. You have some
Eta Q prime, yes.
Eta is prime. So what?
So you can have linear combinations, right? You can have something like UU bar plus DD bar, but you can have also the difference. And here you can have SS bar plus minus. You can have different linear combinations of UU bar, DD bar, SS bar. So you have singlets in that sense. Yes. Okay. So singlet of color, right? So no color. Yeah. Yeah. These are actually unphysical. These are actually unphysical because you have to protect to the physical rules.
What's the exact definition?
Don't remember, but it's either plus minus. So you have UU bar, DD bar. Exactly.
So Q is the one you get in the SU2 case. You have SU2, you have eta prime, no? And this is what's equal to eta Q.
The thing, Javier, is that so this is the singlet part, right? So so it's just you have a QQ bar. How many ways of constructing singlets out of QQ bar? So it's just a positive combination. So you have the UU bar plus minus DD bar, and the same for the SS bar. Now these are not physical yet because you have eta mixing. So you have to still go to the and this is going to be described later.
Okay, but they do not correspond to singlet SU3.
They do, right? Sure, they do because you have
the trace,
exactly
from the trace, the single one.
Exactly.
And then the trace, if you take the trace as part of this matrix, this is the corresponding of 8. No, the 8.
Exactly.
As it is written, if you take the trace, then you have the sum.
No, but yeah. So
this has 9 degrees of freedom. This matrix. The 10 degrees of freedom is the trace, which gives you the singlet. The traceless matrix
is the object. Exactly.
The single is the sum of eta S prime plus It shows you
Exactly.
interview.
Yeah, the neutral ones. Neutral ones. Yes, as it should be.
I guess this is his definition of eta Q prime, etc.
You can have other definitions. There are other definitions. It's not. This is the Beneke Neuberg Sahraida definition. Yes, because there are others. Yes, because again you can use different combinations. Yeah, because also there are different mixing schemes. So
Sometimes it's called eta 0 or eta 8.
that's those are.
And this is the singlet and the octet. But here, this is a linear combination.
Yeah, this is
two. Here I see 4.
No, but you have eta 0, eta 8, and you have also the prime.
Exactly. So the physical one normally. So normally the physical ones are the eta prime, and as Javier said, there is another notation where you can use eta 0 and eta 8.
Okay. So you get from the symmetry.
So it's just different ways.
Sorry, but you also have the eta. So eta 0.
No, just for the symmetry that you get big time. So okay.
Okay. I mean, this essentially come from linear combinations of, let's say, Q1, Q1. So it's this kind of stuff, right? So it's a thing. Because you have the one with the conjugate, the same one. So it has to be always neutral. That's why you have always only neutrals in the diagonal. Also. Yes, so it's always flavor singlet, and then you have indeed the charged ones are the ones that come from the octet. But what I'm trying to say is that this expression. So what I'm doing now is I started from the amplitude and I said there are two sectors depending on the Siegen structure of these factors. And now I'm going to focus on the first one. So, but the only difference between these two guys is just the Siegen structure. And in terms of SU3 flavor doesn't care about the Siegen structure. So then what I describe for the first component here has also to be true for the second component. So I'm just going to describe how this amplitude then can be described in more detail using this SU3 flavor symmetry. That's what I'm trying to do. So you look at the T part, considering that you have a P, and considering that in the SU3 flavor symmetry, the P part is a vector, and the P part can be written in terms of this matrix, then you can decompose TAD in terms of this expression. Looks a bit cumbersome, but it's not that complicated. So the idea is you can follow the equation. You have the initial VI that goes into two M's. That's the general message, and that happens for all the terms. You always have a VI and two M's. That happens because you are describing this transition P to P. So there is a matrix M for every P, and you start with that P, that is a vector. You can see that it's a vector in the equation because the vector has only one flavor index. These are flavor indices. Now, the M has two indices because it's a matrix. And the next thing you do is you have to, so this T, this tau here, comes from the physical amplitude, and the physical amplitude has to be neutral in the flavor symmetry. So then you have to contract all the indices. Then you have to introduce an extra matrix to fully contract all the indices, and that matrix is precisely this H. And you look at in how many ways you can do these contractions. This is precisely how determines all the terms in this expression. So you look at the flavor symmetries and you look for all the possible ways of contracting all the SU3 flavor indices. And that's what you find. You have 10 terms. And as I said, this is just mathematics. This is just creating SU3 flavor singlets out of the physical states. Okay, but as I said, this only holds for the tau. But the only difference between the tau and the P is the Siegen structure. So this same rule also holds for the P. So this holds for the tau TDA, but it will also hold for the P TDA. The key difference is that these coefficients that add together with each term are going to be different for the T and the P. But there's going to be a mirror term. For example, you take this term, there's going to be a mirror term for the P as well. There's a very economical way of describing all these processes. Look, I can describe all the final states with this single expression. So it's very powerful in that sense. Of course, you have to determine what are the values of these T, C, A, E, and so on.
This is just with big Nareka. No? This is the same thing. No? This is big Nareka. This T, C, A, and so on. These are reduced matrix elements. No? Same thing. There's no difference. No?
These coefficients here? This T, C? No, well, they are encoded the physics. So this comes from phenomenology. These are not.
This is what is called typically
the Wigner-Eckert, Javier, will come from the H.
What?
The Wigner-Eckert coefficients, the ones you are referring to, the symmetry factors, those will come from this, from the metrics that allow you to contract all the indices. So those come from here. Again, like you have a B, you have a 2 M's, you have 3 indices, and you have to make singlets out of them. So then you introduce this matrix H. This is the matrix that will encode the coefficients you are measuring. But then you have a fully contracted term, it's just mathematics. So you need to put the physics inside. So this comes from this coefficient. You see what I'm trying to say? This is what they call the reduced matrix. This, for instance, will have contain information on each element. But you see the idea, the only thing I'm doing so far is taking into account the symmetries, writing the amplitudes, considering these symmetries. Okay, so this is just so far mathematics, and then the physics will come from these coefficients.
Okay. So this is an amplitude.
This is a.
It's an amplitude.
Yes.
So it's not about.
It's not that.
It's not about. So
no, it's just what you will find when you calculate the physical amplitude. Yes.
What do you mean by BI?
Which coefficients are they? This BI?
This BI, because
this is just this.
Yeah, but these are not fields. What are they going to be? Yeah.
I'm going to explain so. I mean, so far I am trying to make sense of these
These are states. I mean, this is you have to think about the matrix elements, and then in the initial state, for example, you have a triplet, no?
Yeah. But this is going to be a number for.
This represents a triplet of states, and then the M's represent an octet of states, and then you put the ritual, you do the theory.
Yes.
Clear, but that's not going
so let me explain. So for example, yes, exactly. So for example,
on the numbers are unknown.
No, these are Clebsch-Gordan coefficients.
No,
they come here. The Clebsch-Gordan come from here.
I think the Clebsch-Gordan is the whole thing.
Probably I think you're right. Yes.
So B, H, M, blah blah blah. This is the Clebsch-Gordan coefficient.
Yeah.
He's breaking it in a very complicated way. But
this is
just the Clebsch-Gordan.
But this is just the prehistoric way. This is all notation from the 80s.
Sure. This doesn't.
Yes, it's from the 80s. Yes. No, I think I agree with you. The full symmetry stuff comes from here.
So this is Clebsch-Gordan times reduced matrix elements, and the reduced matrix elements are the one in red, and all the other ones. And this is a convenient way to take the matrices and so on and combine them together to understand.
But it's a very convenient way. Let me explain why. So I think this may address your question. So for example, you want to see what are the coefficients for the process B plus going to pi naught A plus. Then what you do is you take 1 here, all the other entries to 0, because that's for A plus. And then in your matrix, you take the pi 0 entry to 1, and the K plus to 1, this one here, and all the others to 0. And then you just make the algebra to work, and then you see exactly what is expansion. You see what I mean?
Yeah.
So it encodes everything at once, just by looking at symmetries. So that's very powerful in that sense.
Okay.
So that's the idea.
So in this case, M, so M in this case, for you, would somehow contain both mesons. The single matrix M would contain both mesons.
That's why you put two M's, because you need two. Exactly.
You don't put them 1 and 2, you put the same matrix, because
exactly.
Both, you put 1 in the pi and 1 in the K.
Exactly.
Okay.
But you put it twice, right?
All right.
And that's what I said. You need a singlet. So this a singlet out of the full thing, because the physical amplitude should be flavor neutral. So then you introduce methods to contract all the possible flavor indices. And
but then you have to tell me what is H bar, no?
H bar? This one here.
This is the Hamiltonian. You have to see.
Well, it sort of comes from there, right?
You have to see which terms are that violate the flavor symmetries and so on. Now you have to read the operators. You have to see what the
You can read it from there, but let me. I will show you how this maps, for instance, in QCD factories. That's one of the targets of the talk. Okay, and now that you have this expression, the interesting thing is that you can actually represent these things pictorically. So, take for instance this term over here. This is related with this color allow tree topology. It will correspond to this one. So the idea is that you take, for instance, the index I here. This index I color flux to the meson. So that's precisely what you are having here. This flux to the meson, and then the other indices for the other M fully contract with the H. So that's why you have some kind of they converge to the same point here. So the H, you can think in the H as being here and absorbing all the flavor indices from the second M, whereas the B and the M share one common color line. Oh, sorry, flavor line. And then you do the same thing for all the others. So the point is that this seemingly complicated expression has actually a very nice pictorial representation. So each term can be associated with one topology. So that's why this is called a topological representation of the amplitude. So everyone, so you just follow the same rules. Just check which indices contract with which, and then translate that geometrically, and you find all these topologies. Okay. Needless to say, this is not all the topologies were included until 3 years ago. Did I understand correctly? People were missing consistency on topologies, for example.
So what happened 3 years ago?
So they found out. So I will get there. So okay, but there is now that you have all this language in terms of SU3 flavor, I have never looked at irreducible representations. So far, I have just looked at indices that contract fully to get flavor neutral states. But now you can look at the symmetries in more detail. So you can think in decomposing this flavor structure, the H, into irreducible components. This is what people from the 80s were doing. So they always look at this expression, but in terms of irreducible components. So then so now you have this H in terms of this S3 irreducible, you can just translate. I mean, okay? So as I said, in the previous case, you need 10. So here you will also have 10 different coefficients. The physics, as I said, you see in these terms underlying red. They are going to be different because you have two representations. You have the TDA, the topological, and now you have the IRA, that's the irreducible. But the information is the same. The information is the same. Okay? Right. So, as I said, there were the equivalence between the SU3 and the topological was not complete until 3 years ago. That's what happened. So in this paper, they found the full dictionary. They found that there were some topologies that were missing, and they found the full match. So as it should be, because it's just two different languages to describe the same physical system. They found a dictionary that tells you how the topological physical coefficients that are on the right-hand side of the equations translate to the SU ones that were very well known.
So how many parameters do you have?
I'm gonna get there, Javier. But I can tell you now. I can tell you, yes. I can tell you.
Just let me.
I can tell you.
So you have the ones for T, the ones for P, but then you have each one here, T,
10, it has 10.
But then you have to multiply by the number of reducible representations.
It's easier than that, Javier. So if you look at all the possible contractions, you have the T, TDA, and you have the P, TDA. Okay, and as I said, the only difference in the mathematical aspect is just the CKM. So for purpose of symmetries, they are the same. Of course, the difference is going to be in the practical case, the difference is going to be the TSS. You don't have a PSS for the P and a TSS.
Yeah, you have a T for the T and a T for
exactly.
the T.
Yeah. Now I'm getting there. So now there are 10 terms. Yes, wait. This is very important, and this is going to be one of the key points of the complex.
10
times 2 because it's a complex.
And times And times the number.
And then you have the same here. You have 20.
Times the number of irreducible representation.
No, Gary, but you don't have to mess with that because you have 10 here. You have 10 here in this language, right? You have 20, 20, you have 40 in total. And when you change to the irreducible representation, you already know what is the transformation. You don't have to, it's just this, it's a linear combination. So you just put these in the equations, and you have to still have the same number.
Okay, this is what I was saying. So you know, and how do you know this? How do you know this? Because
What you just do, I mean, you have a
I understand.
one command sense, right? In table, you use the composer.
Sure.
It's not a problem. So you have 40, okay? But now this is a very important question. I'm glad you asked because I want to address that soon. But okay, the point is that this has to do with your questions as well. So if you want to know what is the, I mean, here, so B minus, you want to describe B minus going to pi naught, pi minus. From the 3 side, the only thing you need is C15P. So the amplitude will go as 4 times root square of 2, and then the coefficient that is C15P. That will be from the T side times some CKM element, and then you have to put the P side, that is the same. It's the same coefficient, but instead of a T here, you have a P, C15P. So this is how powerful it is. So you want to write another state, for example, I don't know, this one here, BS to pi naught, you follow the same game. So the amplitude for BS going to pi naught is going to be just, you read the coefficients. So then it's going to be a 2 multiplying A3T, and then nothing in the others, and then you have a 2 plus 2 multiplying, so I'm looking at this line, the A15T times the CKM element plus, on the P side is exactly the same, but instead of a T, you have a 2, same thing. You have 2 times A3P plus 2 times A15P times the corresponding CKM element. And that's it. And you can code all of them using these powerful formulas. You have to include then the etas, you have the mixing, you have to define a scheme. So we use the scheme that Thorsten, Kroll, and Skate introduced. That it's by this term theta FKS, mixing angle. Okay, now this is indeed a very powerful description, but it is very passive. So it's very passive in the sense that this doesn't tell you how to calculate these coefficients. So far, I have just described passively how to express these amplitudes, but without telling you how to calculate these coefficients that actually encode the physics.
You have beta prime.
What is that?
No beta prime.
But these are the physical ones. So you have to consider the mixing. So you know how, I mean, the eta primes, you want to calculate stuff in the physical sense. Let's say B naught to eta. This is going to be something like the amplitude corresponding. So the amplitude of B naught going to eta. It's going to be a linear combination of B naught going to eta q multiplied by some trigonometric function plus a of B naught going to eta q prime multiplied by another trigonometric function. So it's going to be a mixing, like in Playboy mixing, like 2 different amplitudes. So these are still the unphysical. These are the unphysical still. The physical would be the eta prime, as you said. But I can construct them out of
just because I was just confused by the thing he said. You have also eta q prime. No problem.
Okay. So, I mean, Javier, for the eta q prime, there's not a big problem. I mean, indeed, you're right. So there are no the eta q primes. So the eta q primes, there are no problem. They can be also obtained automatically because the eta q and the eta q prime are in the same thing. So everything happens for the eta q is also valid for the eta q prime. That's why I didn't include them. You see what I mean, Javier? Look, the eta q and eta q prime always appear in the same way in the metric. So whatever you calculate for eta q,
and that's why it seems redundant.
but it's not because then when you have the mixing, you have two different contributions with two different angles. One is going to have the cosine, the other is going to have the sinus, and you need that because there are two physical states, the eta and the eta prime. So it's not redundant. Okay, so as I was telling you, so far I have just described passively how to parameterize the scalar. It has been just parameterization based on plane symmetries. I haven't tell you how to calculate the coefficients, these coefficients that actually come from the physics. And in the absence of anything else, there is no way. There is no way to do it. What people from the 80s started doing was to parameterize these expressions, like I said, and then extract these coefficients from data. You can find papers, old papers where they start doing that. There is also a recent paper by, especially the Chinese, were very interested in doing these peaks. I think the most recent paper is from 2015 or so. But what you do is you use physical quantities, you use branching fractions, and you use CP asymmetries to extract the physical coefficients. Okay? Now here comes the detail of the degrees of freedom again, Javier. So as I said, you have 10 times 2 because they are complex, plus 10 times 2, so you have 4 in total. But once you do the physics, it turns out that there are some linear combinations that always appear together. For instance, this and this. That tells you that you can get rid of the one of the A60. But whatever happens for the T's also happens for the P's. So then you can get rid of two complex quantities, the A60 and the A60, meaning that you have 40 minus 2 parameters times 2 because they are complex. So then you have 36 degrees of freedom. But then you can absorb one phase, global phase. So then in total, minus the global phase, you have 35 degrees of freedom. But then you have to put the mixing back. So then you add another, so in total you have 36. And that number is very interesting because actually Martin Benecke was, I'm going to tell you soon why this number is very important. Because what I did with Tobias, had to get exactly that number of degrees of freedom. That's something that Martin Benecke suggested in 2019. But I think Tobias and myself in this paper, we sort of give another argument for this within QCD factorization. So any formalism that describes this kind of decays has to have those 36 degrees of freedom. That's a message. Okay, so then, as I said, there is no way, in the absence of anything else, there is no way to extract those physical quantities, but using a fit to data. So that's what we did as the first stage. So what we did was a fit to data. We used random sampling here, the details of how we did the fit. So we calculated something like 1 billion points in total, and we used sequential least squares in Python to find an absolute minimum. So the idea is that you don't know what is the minimum. You have 36, 35 parameters. So then you just populate this 36-dimensional space with points, and then you do that 1 million times. Okay, and out of this 1 million times, you check what is the value of the chi-square. You take the 5 best values, minimum the 5 minimums out of this just force brute evaluation. Just populate the space with points, and then you evaluate the chi-square, and then take the 5 minimal values of the chi-square. Okay, and then you use these 5 points as starting points for a more sophisticated search algorithm. And you repeat this 1,000 times, so in total 10 to the 9 points. Okay, and that's how we obtain the minimum for fitting this parameterization to data. And as I said, there are 2 languages. This is the topological, and this is the symmetry. So you can do this in any of the 2 parameterizations. So this is what comes out. So one of the key things I wanted to address in this project was the determination of the topological, or the annihilation topologies. So one thing of interest were these topologies here. And they are of interest because QCD factorization cannot tell you what are the values from first principle. So that was one of the keys. But so far I haven't talked about QCD factorization formally during the talk. But one of the key points was to obtain from the fit how sizable are these contributions. Okay, so then the important thing is that
a non-technical question.
Yes.
So when you feed these 36 parameters,
Yes.
the data,
Yes.
how do you start? Do you just divide this 36-dimensional grid and you do spacing in its direction?
No, because
You do random sampling.
exactly. I mean, in the absence of any extra information, every point is as good as any other point, in principle. There were some constraints we used, but okay. In principle, there is no weighted space.
The priors are flat in its direction.
Okay.
The prior is flat.
Exactly.
But you have 36 directions.
Exactly. So just take some interval. I mean, it's what we know is that these parameters has to be between -1 and 1, 1 and 1, right? The modulus, because they are complex. And the phases can be between 0 and 2π.
And you say that you determine them rather than states.
Is it the same?
The values that you plot here.
Well, that's what comes out of it.
Yeah, so it's precision 10 to the 9 state.
Well, yeah, numerically, yes.
No, but these deltas are the errors, no? What is this?
These deltas are the phases.
The phases. Yeah, I mean, what are the ranges and so on?
That comes afterwards. I will tell about that one. Yeah, I will talk about that soon. But this is just the basic point. These are not the ranges. This doesn't include the 1 sigma ranges for this. Not yet. Not at this level. I will talk about that afterwards. This is just the basic value. That's the minimum of the chi-square. Yes. So then what you do is, for each parameter, you take a partition between -1 and 1. You do that 36 times.
Why are this?
No, not partition. Sorry, no, that's not true. You take random values in this 36 parameter. You don't have to do partition.
It's a partition because you read all.
Yeah, but it's random. It's random. General. So you generate random numbers.
Yeah.
You generate 1 million random numbers in this 36 dimensional space. You don't have to do a partition. The only constraint that these random numbers have to be generated between -1 and 1. So you don't do a partition.
But let me just say this. Okay? Well, I mean, I'm taking time.
No, it's fine.
Very interesting discussion. But on each axis, you make divisions.
No, because that would be inefficient. That's the point. So you make
in your head, you can do that.
Yeah, exactly.
Just to see how many points there are. So you want to say 2 to the power of 36 is much more than that. No, it's 1,000 power of 36. It's 10 to the.
Yeah, if you divide that, you consider 10 to the
90. No, sorry, more than 10 to the 100 possibilities.
No, but that's the point. That's why you don't do the partition. So what you do
it's the same thing. That's what you say. It doesn't matter whether you do a partition or you do random. Your head, in your head. So how many effectively how many points per line? So you're asking effectively how many points per line?
No, but look, indeed, because
he doesn't like it. Sorry. He doesn't like that. No. I got something. I might do something.
Okay, no, but I mean, indeed, doing a partition would be extremely inefficient. What you do is just populate the point with 10 to the 6 randomly.
Yeah, that was not his point. His point is effectively, if this
you can also do that, yes.
So his point is, 1 billion points, is that enough for a 36-dimensional space? That's his question. It's not there about how do you do it.
No, that's the point, right? So it's not. Because you're gonna get values that are not really the real minimum. So you're gonna get 10 to the 6 points, right? 10 to the 6 values. And this doesn't guarantee that it's a minimum because we're just doing forced groups. But what you do is you take the 5 lower values and you fit these into a more sophisticated search algorithm. And something like that, insert one of these guys that actually give you a more sophisticated convergence criteria. So
2 questions. Why are these? So you say -1 and 1. I mean, I think you need 0 and 1.
Yes, because the base is
why 1? Why do they have to be smaller than 1?
For physical reasons. I mean, in principle, they can be bigger. But it was. So.
I mean, if it's just for practical purposes,
There is a reason. At the end of the day, this has to go into QCD-factorization. There is a map, and that's what we found, right? So far I have talked about the topological and the symmetry representations. But then, I mean, this is the next thing. I'm going to answer your question, but so that means I have to go a bit forward. Then you have this language, these magical formulas of Mark embedding, right? And you can map these A's and so on into the QCD factorization part. And you know that the alpha 1 QCD factorization is, that's what it comes to. So they should be order 1. Now, if these things are, let's say, 2 or whatever, then the sequential least square algorithm has to find. See what I mean? That's where the criteria comes from. Because indeed, this can go to 300 or whatever, but it comes because we worked out the map, and we know that from the mapping to something that is more first principles based. That's the reason.
Yeah, I don't have a problem with this.
Yeah.
You find small values that's enough.
How do you know you're not in a local minimum?
No, that's the problem, right? So that's exactly. So that you cannot guarantee 100%
Why
all
don't
the
you
time.
do a map of change? This is.
No, but also with a map of change, you cannot guarantee that you are because you can get trapped, right? You can always get trapped in a.
This is a 4th degree polynomial. Now that you have these guys squares, so the amplitudes are squares, so are degree 2 polynomials of these guys.
Yeah.
And then the chi-square is the square in the amplitude. So you know this is a degree 4 polynomial. It's not a complicated function.
No, it's fine. But I mean, you can use any algorithm. I mean, so again, like what we used was this sequentially squares. And the reason why we use this because we could easily implement the extra physical constraints of this. But you can also Markov change, yes. And it has to converge. I mean, actually, we used 2 different algorithms, and they were giving roughly the same answer. But in the other algorithm, we could not impose the physical constraints. I mean, you can use because Python gives you a big collection of minimizers.
The physical constraints what are the physical constraints? Not just the amplitude.
No, because some of these channels, for example, some of these channels have not been measured. So, but you have inequalities, so they have to be less than. You see what I mean?
In bounds.
Exactly. So that's a constraint. So they enter in that, and sequentially squares allow us to implement that. That's the reason why we decided.
Isn't that just coming to a chi-squared, right? Isn't that just just telling you something about what your chi-squared function is? It should match to the minimization function. What your
but the thing is, how do you put that? How do you put a bound? I mean, how do you put a bound in the chi-square?
You say.
So how do you impose this bounds? Is this a sharp cutoff, and then you impose that this observable is sharply bounded by this experimental bound, or you know that the experiment is.
So these are the bounds, right? So these are some bounds, right?
Yes, but you impose this sharply, no? You say.
This should be less than.
Sharply.
Well, the experiment usually tells you this is a branch ratio at like a 90% confidence level, right? So yeah, but so you can put that in your code, Joey.
I think it's probably easier to do it well with the.
No, wait. So let's see. You have.
I mean, the experiment usually is
actually. You have theoretical minus all experimental, right? You have something in this measure over C. That's how you construct the terms in the chi-square, right?
Yeah.
Now, if I have an upper bound for this guy, right?
Yeah.
How do you put that in the chi-square? There is no symmetry. There is no symmetry, right? I mean, you can include that, and that's what that algorithm allows you to do. So when I include the minimization, as you said, I want that these branching fractions are below this.
You just add. So let me tell you what you do. You add to the likelihood the one from the bound. So the chi-square is a product of likelihoods of all the different measurements. So you just have to include an extra factor to the likelihood, which is given by this bound is really a likelihood.
No, but that's fine. No, it's exactly, but that's what the algorithm is doing automatically for me. So I don't have to worry about that. I just put everything that I know inside the chi-square, and these sequential least squares allow me to put these constraints as an extra thing, and it does what you are saying at the end of the day. But I don't have to do that by hand. You know what I mean? So I don't. So the algorithm, I just tell the algorithm, just respect these bounds. Okay. So that's yeah. Okay. So then the point is that you find the minimum. Okay. Now this is the goodness of the. Okay. So it sounds I think it's not good.
You should finish in about 10 minutes.
Okay. So these are how this is the description of the data. So most of the experimental values come between that sigma. Unfortunately, some of them have big errors. That has to do with the fact that we have the bounds, and also some quantities in the experimental side have also huge uncertainties. Okay, so these are now the basic points plus the the errors is one. So that's the best way to visualize them because they are 2D. That's the complex space.
This is what 60%.
So yeah, I mean, where do you look at? So for example,
it's a confidence level ratio.
So 20%, right here, 20%.
No, I mean, these are confidence.
Yeah. 1 sigma. Sorry, 1 sigma. Right? Sorry. Yes, 1 sigma. Yes. Okay. So now, so far, the only thing I have done is parameterize, extract items from data. Now let's go to a more fundamental way of calculating these things. This is really the reason why Tobias and myself did this. So there is this technique called QCD factorization. It was a very famous technique developed by Martin Benecke and friends. Yeah. Okay. So it allows you to calculate it doesn't go through all this mess in principle. It doesn't look at these quantities. It gives you an alternative way of parameterizing things and calculating things from first principles. So here I have to fit to the data. So as I said, this technique gives you a solid quantum field theoretical tool to calculate all these amplitudes from first principles. So the idea is that you have this transition, for example, between the decay pile and the matrix element of an operator contributing to this process can be decomposed in the nice sense in this way. So you have the form factor.
So do you really think that the QCD factorization is more fundamental?
No, wait, I get into that point. That's precisely the point of this. And then you have the decay.
I want to hear his question. More fundamental than
Your method.
No, wait. I'm getting to that point. Wait. So it gives you these expressions to calculate, as I said. So naive factorization tells you this. So you can factorize this diagram in terms of a whole factor and decay constant, but it ignores, for example, this exchange and plugins. So this is the formula of QCD factorization. So the first term is the naive. It contains a special case of the naive factorization case, and the second term. Consider this spectator communication between the decaying, the emitted meson and the spectator quark, so spectator scattering. Okay, now this technique considers the heavy quark limit, so it actually considers the mass of the bottom. It takes advantage of this fact that the mass of the bottom is bigger than the lambda. Actually, in the formal limit, you take MB going to infinity. Okay. And now you are talking about specific bases, you're talking about operators, because now you're calculating everything from first principles, fine. Okay, now in this formalism, you have this decomposition for the amplitudes. It looks different to the one we used before, but it's not quite different. I mean, at the end of the day, you have still the P, the M, the M. The difference, I'm not writing the components explicitly, but you can still write this how you say, all these indices, flavor indices. That's not a problem. So here, I just not writing the flavor indices explicitly. This is the formula that Martin puts in his paper. But the idea of this formula is the same, that you can basically split a physical amplitude in terms of these alphas and these betas. Now, what is the problem? The problem is that there is a problem here. The problem are these topologies. And QCD factorization doesn't tell you how to calculate. So these topologies are encoded in these beta coefficients, and they appear in all these channels. So even if you can calculate the alphas very precisely, these betas cannot be calculated with QCD factorization. That's the problem. So then what you have to do is, okay, the first thing is that you find that these contributions, you find arguments to establish that these contributions have to be power suppressed by this lambda over NP. And what Martin and friends did was to introduce a educated answers on how to parameterize this. This is the parameterization they have been using from 2000 and 2003, and it hasn't changed since. That's the problem with QCD factorization. These power corrections, this annihilation contributions.
There was a paper recently where they calculated this problem.
Yeah, but they use that's from some Chinese people actually. Yes, but they didn't use the heavy quark limits. Actually, this was under discussion. We invite them for the workshop. Some people in Siegen are not quite convinced yet about this. So Guido Bell has some things that he don't like about it. I already recorded, unfortunately. But I mean, he had some objections about, so some comments, if I understood correctly. Also, I don't want to say things wrong, but yeah, so it still has to, it may be correct, I mean, but yeah. There are, people in Siegen are not, they want to discuss this a bit further. Tobias, for example. Okay, so then what can you do? So then the idea is to profit from the feeds we used before to get information on this annihilation contributions. That's the idea of this project. Okay, so then the first thing you have to do is to establish a dictionary between all these SU3 topological and this notation that Martin Benecke and friends are using. Okay, so that's what we did. I don't want to go to the details, so it's a bit technical. But the important thing is you can find that dictionary. And you can use also information that you already have from the calculations. So, I mean, some of these alphas are very precise determined. You can use that information also. And at the end of the day, you find this dictionary that translates the topological to the QCD factorization language. So here is the QCD factorization language, the alphas and betas. This is the topological. And since you have the dictionary from topological to SU3, now you can go in between any bases. Okay? And now what you do is you take advantage of the fit you did and map that information into these amplitudes, the QCD factorization amplitudes. And now you can see how big these betas can be. So they are, for several cases, relatively small, 4%, but for other cases, it can be sizable, 30%, 20%. That's what data is telling you.
So this is the same plot you showed before, but
now map out into the QCD factorization.
Instead of T, B, and so on, beta.
Exactly. Now these are the betas that QCD factorization can calculate. Exactly. That was the idea. To see how much can we learn from data, considering that these betas cannot be calculated from first principles. So see what data tells you. What I mean, for some cases they are not small, but also you have to consider the data is not so big.
Are you using the calculation for alpha and so on?
Yes. What I am using, the only thing we used was the fact that the alpha one is very precisely determined.
So did you use?
That we use. That's one of the constraints on the field. Yes.
Only alpha one?
Yes, not the others.
For pi or for everything?
Well, we sort of, here you have to use SU3 symmetries. We assume you cannot, otherwise you have too many parameters. Yes, SU3 symmetry. Yeah. I mean, if I understand correctly, I mean, sort of Martin Benecke got this original idea somehow, and then but then Tobias and myself just developed the thing.
You put to zero the stigma annihilation, expectation scattering, and so on. You put to zero.
No, but that's not a problem, Javier, because you don't care about that. That's already accounted for. Because you have this, for example, look, let's say the alpha 3 that has this particular scattering or whatever maps directly into the PC, and the PC you obtain from the fit. You don't have to be worried. You don't have to be picky about each one of the contributions. All the contributions are at once included because you never care about that when you do the SU3. You see what I'm saying? So you do the SU3.
Maybe my question was, do you impose that these 3 P's are zero?
What was that?
TPA equals 0.
No, but that comes automatically. That comes automatically from the fact that you take, for example, the betas. The U and C the same. That's for example that's an assumption in the papers of Martin and friends. For example, that's used.
Yes, this I understand. It comes from the fact that betas do not have contributions from the payment with different quarks. Yes.
Yeah, and this automatically goes yes. This tells you that these quantities
are doesn't give you 0, it's your range. Then you have to say no. This is
because what, sorry?
The fit you did before doesn't give you 0.
Not per se.
Now you impose
exactly. To further constraint. Exactly. Yes. And yeah, so this is what comes out from the annihilation side. And as I said, the idea was to see how much can we learn from data about these annihilation contributions that cannot be computed from first principles. We have to develop all these mathematical techniques, okay, that are not really that, I mean, it's just playing with SU3 in flavor indices and a bit of matrix decomposition over there.
Do you extract